The same rules discussed in the previous sections for indefinite integral also go for definite integrals. Except this, there are some properties that related to the limit of integrations will be specifically applied to definite integral. So these are some properties here. The first one, for the integral which has a limit from a to a, means that they have the same upper and lower limit, then we will get the answer which is equal to 0. So for example, integrate 3x from 1 to 1 will return 0 because the upper and lower limit are the same. So we may say there are no region exists under the graph of 3x. So we can actually, let's say this is y equal to 3x or fx equal to 3x. And if let's say it is from 1 to 1. So what we have is just here, in this case, there are no graph exists between the interval 1 to 1. Second, the integral of fx from a to b will be equal to the negative integral for the limit of integrations from b to a. So for example, I have this as we have the integral of x squared from 1 to 3, which we get 23 over 6. Then I do the integrations for x squared from 3 to 1. Then we should get negative 26 over 3. And if we add a minus in front of it, so we get back 26 over 3. So the computations for integral of x squared from 1 to 3 and negative of x squared from negative integral of x squared from 3 to 1 will contribute to the same result. Third, if c is in the interval from a to b, then the integral for f of x with a limit from a to b can actually break up into two integrals, from a to c, then from c to b. So for example, let's say I wish to find the integrations for x squared. I can solve it from 1 to 2 with the integral, and then from 2 to 3, and the sum of this actually equal to 26 over 3. So this is exactly same with our computations before, where it is the integral of x squared from 1 to 3. If we look at the figures, concept is like this. The integrations from the limits from 1 to 3 can break up into 2, which is from 1 to 2 and from 2 to 3. And definitely if you want, it can be from 1 to 2.5, from 2.5 to 3 also, doesn't matter. This is the so-called additive properties for definite integral. Fourth, if the functions of f of x is larger than 0 in the intervals of a to b, then to integrate f of x over a to b, it will be larger than 0 too. So for example, let's say we have f of x which is equal to x squared, okay, where it is larger than 0 on 1 to 3. So the integrations for x squared from 1 to 3 is equal to 26 over 3, right, in our previous computation. So this is larger than 0. In the reverse case, if f of x is less than 0 in an interval of a to b, then the integrations of f of x in the interval of a to b will be less than 0 also. So for example, we have f of x equal to negative x squared, let's say on 1 to 3. So which is always less than or equal to 0 in this case. Then the integrations of negative x squared from 1 to 3 will return negative x cubed over 3 from 1 to 3. So it's negative 27 over 3 minus negative 1 over 3. We will get negative 26 over 3, which is less than 0 as well. Number 6, if let's say we have two functions, f of x and g of x, and f of x is always larger than g of x on the interval of a to b, then to integrate f of x in the interval a to b, it will be larger than the integrals of g of x from a to b. So, for example, we have the computations of this. If let's say I integrate e to the x from 0 to 2, I get 6.3891. And I integrate 1 from 0 to 2, I get 2. It is clear that the integral of e to the x is larger than the integral of 1 in the interval of 0 to 2. So if you look at the graph, the orange line is gx equal to 1. So this is the regions for under gx equal to 1. And the blue line is the graph for e to the x. So the regions for the region under the functions e to the x is this. So in this case, we will say if f of x is larger than g of x, you can see the graph itself is larger of g of x in the interval of, let's say, 1 to 2. So then the integrations of f of x will be larger than g of x as well. This is the constant multipliers rule. Let's say I have a constant k. This k is multiplied to f of x, and the integral of k times f of x is actually, I can take the k out and then times with the integral of f of x. So for example, I have the integral of 3x squared from 1 to 3. This one will return 3x cubed over 3 from 1 to 3. So it is equal to 3 cubed minus 1 cubed, which is equal to 26. This is equivalent to our computations previously, where this one is actually equal to 26 over 3, and hence we will get the same one. The last one is a sum and difference rules. Let's say I have two functions, f of x and g of x. The sum of all the subtractions of them, we can actually do them separately. I can do the integrations of fx plus or minus the integrations of gx. So let's say, for example, to integrate e to the x plus 1 from 0 to 2. So in this case, I'm going to get e to the x plus x from 0 to 2, which is e to the 2 plus 2 minus e to the 0 plus 0, which will give us 6.3891 in this case. So we have actually done the computations for e to the x and 1 previously, which we have 6.3891 and 2. 6.3891 and this is 2. So it means that for this case, if I do it separately, then I sum them up and I get 8.3891, which is same with the previous one. So this is the sum and difference rules.